Hey physicists, we're looking at 5.2 electric current. Try this little warm-up first. It's from topic 1 about uncertainty and such. I think we're a little rusty, so I'm just trying to throw those in here and there. Pause me and go. Okay, so this is an old exam question. A student measures radius of the circular plate, trying to find the area, and figures out it has a certain uncertainty, an absolute uncertainty. So a circular plate looks like a circle, and we're measuring only the radius and trying to find the area. Okay. So the area is related to, well, the area is pi r squared. Pi r not squared, pi r round. So they're measuring the radius, and the radius has an uncertainty of delta r. So the area's uncertainty, well, the fractional uncertainty is based on how uncertain we are about the r. Now there's some formula guidelines in your booklet which look like this about how to combine these. And so this is talking about the fractional uncertainty. Fractional uncertainty is the amount that you think you might be off divided by the overall value. So we would have some uncertainty over r here. This really is, the pi is a constant, so there's no uncertainty in pi, but the two values that we are uncertain about is just like the a and b. It's r times r. I'm uncertain about both of those, so we're kind of doing this. We're adding our uncertainties. So the uncertainty in the fractional uncertainty about the area is going to be delta r added together twice. You have two sets of them. They're being multiplied here. So the uncertainties will add. So your fractional uncertainty would be delta r over r plus another delta r over r because you're multiplying them. Common denominators, add them up, so you get 2 delta r's over r. This guy. Oh, I should have used that. I should have used capitals. Cool. So there's your. I think that's your fractional uncertainty. Yeah. Great. A. All right. Moving on. Homework questions? No. Good. Fine. I want you guys to walk out kind of being able to understand what electric current is. I'm sure you understand some of that already, but we're going to use some more specific terms. So we looked earlier about charges moving, and charges move from high to low potential. Maybe let's clarify that about positive charges. All right, positive charges move from high to low potential, so they'll be repelled from these like charges and be attracted towards these negative charges. But that only happens if these are actually free to move. So if it's a charge sitting in the air by itself, floating, or it will be attracted or repelled. It can only do that if it's in a conductor, right? Or free to move, right? Free to move. And so conductors are materials that allow charge movement freely. Metals do this quite well, like the electrons in their lattice, just how they're made up, allows them to move. That's a little deeper. The material science is deeper than we need to get into here, but it's great chemistry about how they share electrons. That sort of bonding pattern helps them transfer the electrons without any structural issue. We call this conventional current when positive charges move down the potential gradient. So they move from high potential to low potential. That's conventional current, the little positives moving along. But really, and they started doing that because when they were first studying charges, these are a lot bigger and they're a little bit easier to detect, where electrons are much smaller, faster, harder to detect. So they didn't realize initially that the electrons were the ones moving. Now, we know that for the Bohr model of the atom is heavy protons and neutrons in the center and the fast electrons whipping around the outside. And those are have much more freedom to move, right? And so they're the more mobile, and so they're really the ones moving through these electrical circuits. making electrical current. This is, this makes sense that if these are floating in space, that this positive charge would move away from the positive, it would be repelled from the positive and be attracted towards the negative. You could also visualize it if it was in a bar of metal, that these positives would have a really hard time moving because they're at the center of the lattice, and it's the little negative electrons that kind of bounce and jostle their way through, right, and move towards, they're repelled from their like charges and they're attracted towards the positive charges. So they don't just go, there is a potential difference, but they don't just go screaming in acceleration towards the positives. They bang into all of these positive charges, right? And so they hit the atomic lattice. They transfer some of their kinetic energy from motion into, when they hit something, that momentum actually shakes these other molecules, heats them up, right? So they change some of their Ke for temperature, and that's why resistors get hot. We'll talk about that a little more later. But they're giving up energy as they go. Boom, 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 boom. We don't need them to be going fast. We just need them to be moving. And so this is the idea of drift, that they like bounce. They don't just accelerate. So it might look like this. This is a nice little GIF where they're kind of rattling through and moving towards, I guess this should be this way. Right? They're rattling that way, and backwards. An insulator is a material where the electrons aren't free to move. It doesn't mean there's no electrons. It just means that they can't move as easily. Plastics do this. Ceramics do this. Non-metals. And that has no free electrons to move as easily. So current is just like water, like the flow of a river is the current. So high current means it's either moving very fast, like we're moving a lot of water really fast, or it's like a really wide, like the Rus isn't going extremely fast, but it's just a big mass of water, and you get in, there's a lot of current. It's moving a lot of water per time, right? So something with current is a lot of water. It's about the amount of water you can move over time. And so you're either moving a ton of water, or you're doing, or it's high velocity, which means small time. The same thing applies to charge. We say that the current is flowing charges, but it's how the charges change in motion over time. So this I stands for current. It's measured in amps, amperes, amps. A. And it's how many actual little charges are moved along over time. So it's, and each charge has each charged particle that's moving has a certain amount of charge. So this is really, amps is measured in coulombs per second, right? Charges per second. There's another way to think about this that is a little less standard, that I don't love very much, but it's this formula. This is in your formula booklet, which talks specifically about the number of actual particles, the area you're moving them through, how fast they're bouncing through the drift velocity, and also its charge. Basically, it's the same thing. You're looking at the charge moving over time through a specific area. So these are two ways to measure current. Yeah, jot those down. Scenery change. So some of the things that can influence resistance are the length and the cross-sectional area and the resistivity. It's sort of like density. And that hopefully makes sense. I'll show you this demo in a second. But if you're trying to push some charges through this pipe, pop them out the other side, that. One thing that could help you is having a larger diameter, right? So this has a certain diameter. This has twice the diameter, or maybe we should say the area, right? Because really it's the area that counts. So twice the area doesn't necessarily mean doubling the diameter, but we have twice the area here, so you'll get half the resistance of pushing this same set through here, right? So as the area increases, the resistance decreases. Yeah. Another thing that might hurt is if you have to push those through a longer tube. This tube happens to be twice as long, right? You get resistance here. They're banging into the molecules right here. They feel some resistance before they come out. They're going to feel twice that much, right, before they come out because there's twice as many atoms to hit. So as the length increases, the resistance increases as well. The other thing that changes is the resistivity, which is like how dense maybe the material is. You could think about it that way. How often these molecules are going to run into things. So if this has I don't know, just a couple of particles to bump into, these won't hit them as many times as this, which might be a lot denser and has a lot more particles to run into. These are going to feel much more resistance. So that resistivity, specific to the metal, you can look it up or we can calculate it. Higher resistivity, higher resistance, resistance, you'd say. So resistance in a wire, this is a FET demo. If you want to try it out, you can look it up there. It'll be on the Schoology page. If we increase the length, ooh, it sounds too short, right? Small L, small resistance, long L. You can see that there's more dots to hit, right? There's more dots if we were going to send our charges through here. Same sort of thing, if we decrease the area, you're more likely to hit those dots, right? If we increase the area, there's much more space to avoid the dots as you pass the charges through. If you're like throwing a ball through here. And the resistivity is actually like increasing the number of dots. If it's low resistivity, there's nothing to hit inside. This is a superconductor, right? When they talk about superconductors. And this is a really high resistance, something that you would want to make. It's not, this isn't a insulator. This still conducts electricity. It just feels a lot of resistance and gets really hot. So this would be something like the heater, electric heater in your room, or in your oven, that glowing element would be something like this with a lot of resistivity. Neat. Okay. So this is a formula we sometimes use, that the resistance increases with the resistivity, increases with the length, and decreases with the cross-sectional area. Jot that down. We use this kind of lowercase p. It's a Greek letter rho for resistivity. So these are some resistivities for different materials. You can see that copper is pretty low, which is cool. And magnesium steel is pretty high. That's why you don't make conductors out of steel, because it's not as good as copper. So why not just use silver, because it's even better? Well, silver is expensive, and so is aluminum compared to copper. And it's not that good of a conductor. So we use the best conductor for price. Yeah. This is a resistor on a schematic, on a diagram of an electrical circuit. It's just a little box, and then usually you'd have how much resistance it has. So 3 ohms. We'll talk about that in a second. When you open some electrical components up, it looks like this, and you can see these little resistors in here, like that. You'll notice they have little stripes on them, and the color coding of the stripes you can look up in tables, and it'll tell you what the resistance is. So maybe this is like a 2 ohm resistor, and this will be a 5 ohm resistor, just based on what the stripe color is. We use these in a circuit to make sure there's the right amount of current and voltage going through whatever little component we want. So these sort of keep the flow of electrons where we want them. So let's try it out. Resistivity of copper is this. What's the resistance if it's 1 meter in length and 2 millimeter diameter? Try that. Okay, we're trying to find the resistance, the R. We know L, we know P, but they gave us 2 millimeters and not the area. So that's a fussy little bit. So we're going to have to use pi r squared for the area, right? That's like the tube that they're sending it through. It's that flat square area. So cross-sectional area is pi r squared. R is half of this diameter, and we're in millimeters. So then from there we can use this R as rho L over A, and plug in what we know. You should end up with 0.005 ohms. This little guy is the sign for ohms, OHMS. This is 0.0055 ohms. The name of the symbol is omega. It's the Greek letter for Z. Well, I mean, it comes last in the alphabet, so alpha and the omega. All right. So Ohm's Law is this idea. It's talking about how the current flows, how the material flows, based on the amount of push, the voltage, the potential difference, but it's inversely proportional to resistance. So this is the original equation that they were working with, and this is the, if you multiply R, this is the more common equation that we use. So this one's in your formula booklet. Write it down, I'll show you Ohm's Law. The voltage is kind of the push. So it's how much push happens. So if we increase the voltage, we put bigger batteries, there's a bigger potential energy difference. You can see that the current goes up. You get more energy flowing because there's more pressure. Yeah, little voltage, little pressure, little flow. Also, if we decrease the resistance, it's much easier to get current to flow. And so increase in V, increase in I, but increase in R, decrease in I. Yeah. Because the resistance is going to stop the current from flowing. Yeah. But more pressure is going to help. Voltage is like the potential difference. That's going to help the current to flow. All right. So let's use it. What's the potential difference across a 3 ohm resistor? And it's got some, 9 volts is the potential difference. That's the push. How much current will flow? Well, let's use V equals IR, Vir. And we know, they rearrange it. This was actually how they originally talked about it. And so we get 9 volts per 3 ohms of resistance. So therefore we get 3 amps of current moving. All right. If you graph V equals IR, often you get this straight line where, like, as you increase the push, the voltage, the potential difference, you get a linear change in the current. So more voltage, more current, more voltage, more current. Not everything does that perfectly, like filaments in a light bulb. As they get hotter and hotter, the heat makes them more and more resistant. So you get less current flowing as they warm up. So you get a change in pressure, a change in voltage, and initially you get a big change in current, but as the filament gets hotter, that same jump in pressure, voltage, gets less of a jump in the actual amount of energy flowing until here you don't have much of a change, much of an increase. Cool. Just a little side note. All right, that's it. We're doing 6 through 14 out of our practice set, and I will see you later.